So I thought in this video I would just go through the two problems that I pretty much glossed over in class, just in case you needed to see how they were solved. So the first problem is where we're using tangential and normal coordinates. And the interesting thing about these two problems is you'll see that we're using different coordinate systems and different unit vectors, but the motion is really similar in that in both cases the objects are moving in circular paths. So hopefully seeing these two contrasted will also help you differentiate between the cases when you would go to polar coordinates versus tangential and normal. So in problem one, we have a boat and it's traveling in a semicircular path with a radius of 40 meters. At the instant in time, well, not the instant in time, but we find that the velocity actually does depend on time, so it doesn't make sense to say instant in time, but the velocity is 0.0625 times the time squared. And what we're asked to find is the magnitude of the velocity and the acceleration when t is equal to 10 seconds. So when we're doing this, we should recognize that the velocity vector that we write in tangential and normal components is given as the magnitude of the speed, the magnitude of the velocity, which is the speed, times the tangential unit vector. So the first thing we would want to do is to find the velocity, we just take the 0.625 and then we put in 10 seconds to the equation, so we're squaring the 10, and that gives us a speed of 6.25 meters per second, and that's in the tangential direction. Now, sorry, those pens aren't showing up good, so I'm going to have to go over this. So the magnitude of the velocity is simply 6.25. Because it's just in one dimension, we don't have to do any sort of Pythagorean theorem or anything like that. Now, when we think about the acceleration vector for tangential coordinates, we found that today. We found that the tangential component of the acceleration is due to a change in speed, and the normal component is due to the centripetal acceleration, which really is caused by the change in the direction, remember. So this one is, again, relatively simple. The derivative of the velocity with respect to time would be 2 times 0.0625 t, and we'll evaluate that at t equals 10 seconds. And then we want to add the centripetal acceleration component, which would be the 6.25, because that's how fast it's going, divided by 40 meters, and that would be our normal component of acceleration. When we evaluate the change in speed at t equals 10 seconds, we actually find that that is 1.25 meters per second squared, so that's the tangential component. The centripetal component ends up to be 0.976 meters per second squared. And the magnitude of the acceleration is taken by taking the square root of the square of these two, because we didn't really talk about it, but hopefully you've noticed that when we use unit vectors, they are always perpendicular to each other. That's really the only way that it makes sense to designate unit vectors, is to use vectors that are all mutually perpendicular, and that's why we would use the Pythagorean theorem. So for the magnitude of acceleration in this case, we find it's 1.59 meters per second, and again, the velocity was just, the magnitude was 6.25 meters per second. Now, in our second scenario, we have the policeman with the radar gun is at the origin, and he's watching this car go around in a circular path. The radius of the circle is 200 meters. And so because he has to follow the car, the motion of his radar gun as it's rotating will be influenced by the speed of the car. We're told that the angular velocity at the instant when the angle is 45 degrees, that angular velocity is 0.1 radians per second. The angular acceleration is 0.025 radians per second squared. So now when we want to find the velocity vector, in this case, we're working with polar coordinates, so we want to remember how those expressions were written. The radial component of the velocity is due to a change in the radius, and the theta component is related to the angular velocity and, of course, the radius. Now, for our particular problem, the R naught is 0 because the radius of the path is not changing. So we're only going to be left with a theta component of velocity, which is going to be equal to 200 times 0.1 in the theta direction, which is going to be 20 meters per second. And so that's the velocity. The magnitude of it, of course, would be 20. If we wanted to find it, it's only one component. Now remember the acceleration term that we found, because of the fact that when we take the derivative of this expression for velocity, we end up with many terms due to using the product rule, and then we also have to express changes in the unit vectors in some quantifiable way. We can't just leave it as the derivative of those unit vectors. The expression for acceleration in polar coordinates looks like this. And I want to let you know that there is not an expectation that you would have to memorize these. Maybe they would become pretty familiar to you, and you wouldn't have to look at them. You would be able to write at least some of it, but again, this is not something that you have to commit to memory. So here, to find this acceleration given this form, we really just have to fill in the values for all these different quantities. As we found with the velocity, the radius of the path isn't changing, so there's no radial acceleration, so that first term is 0. Then we have 200. Oh, and I made a little mistake because I forgot the square here, so sorry about that. It's 200 times 0.1 squared, and so that's my radial component of my acceleration. Then I have 200 times 0.025, because that's theta double dot. And then for the second term in this theta component of acceleration, R dot is 0, so everything goes to 0. I'm just writing in the values just sort of for reference sake, in case you want to just see how we plugged everything in. So when we work all this out, the radial component of acceleration has a magnitude of 2, and the magnitude of the theta component is 5. And if we want to use the Pythagorean theorem to find the overall magnitude of the acceleration, we find that it's 5.38, and of course the units of that are meters per second squared. All right, so I just thought in case you wish you would have seen a little bit more detail, since we didn't have a lot of time to do these in class, this gives you a chance to see them.